Well, all right. So when we met last week, Friday, we focused largely on the or let's say we solved questions on how to um, determine the external reactions, and then we started by looking at the what we meant by internal behavior. All right. So we described the fact that when you have a beam or any structural member for that matter, when you have an external load acting on that member, let me just do the recap here right now. Okay. All right. So, recap. So, if you have any external loads on a beam or any structural member, so these are the external loads. It could be a UDL, it could be a VDL, or whatever loads we are looking at. Okay. There are usually some supports. Okay. And these supports would provide um, some reactions, right? They could be um, moments, whatever reactions we can have, right? And usually when you have this setup, what it simply means is that the load needs to be transferred through the material of the beam. Okay, so let me just label this as a beam. Okay, so for example, it can be wood, it can be concrete, it can be plastic, it can be steel, it can be any material out there, right? And these materials contain what's the word? Molecules. They contain elements, molecules, or whatever. And these, or usually we say fibers, right? So these fibers within the material are are held up by or they are in a state of equilibrium, all right, which means that they have forces acting on themselves, which are equal and opposites. And these forces, we have three of these. We have the axial, which is the horizontal. We have the shear, which is vertical, and then we have the bending moment. All right. So these internal forces or internal behavior is usually in equilibrium, and there's a reason the material remains stable, or it is as we see it, right? So that if it is a bar of wood, let's say a long piece of wood, it remains that way because the fibers within the wood are in a state of equilibrium. Okay. So these internal forces, axial, shear, and bending moment. Okay. These are in as long as the let's say the fibers are intact. So let me use the word intact for now altogether, all right? So the moment you take the same beam, okay, if you take the same beam as I have above and I cut a section through it, what's what is going to happen? So let's say, let me take this color away. Let me still have the loads as I had them earlier. Let me still have these loads acting on it. All right, just so that we work with some form of uniformity. Let's say I cut the beam into two. All right, which means that I have separated the beam into two parts. It's like just try to take a knife and then cut the, or maybe a saw and then cut the timber or the wood into two pieces, right? That's what I'm pretty much trying to achieve over here. So when I do that, I will have one piece on the left and then the other on the right. So the one on the right will have these loads. Okay. Then the one on the left also have its loads as we had previously. All right. So again, there were these guys on the side. So we just put one here, put one here. Okay. Once you cut it into two, what this simply means is that you have separated the wood into two pieces, which means that you have broken that uh, state of equilibrium that the members were in, or that the fibers were in, which means that once you do that, you end up with these forces. Okay? And these are pretty much the internal forces. All right. So normally the if it's horizontal, wrong, let me just make sure that I use one color throughout. So the horizontal, they'll be equal and opposite because they have to maintain that equilibrium state. Okay. Then we have which this is the shear. Then we have the last bit, which is the bending moment. All right. So usually they will be equal and opposites. All right. So the internal forces are equal and opposites in direction. Okay. Um, and again, when we are defining the structure, we did mention that the structure should transmit loads, right? And also, in doing so, it should not collapse, and also it shouldn't deform excessively. Okay. So if your support can be very strong, they can be able to receive or they have good reactions against the loads. But if the beam, which is supposed to transfer the external load to create an external reaction, is not strong enough, then that will collapse. Okay. Or that can deform excessively. Now the question is, how then do we know if our beam is adequate or has enough capacity to transfer the loads? Okay. So last week I used the like a person as an example, someone carrying a bag of cement on their heads, right? So the bag of cement is seen as the load, the ground is seen as the support, which will provide the reaction. Okay. But if the person carrying the cement is not strong enough to carry the cement, it's not so much about the ground, but now it's more about the person. And if the person cannot carry that bag of cement, they would fall under the load. All right. And usually the load gets transferred from your head through your neck, through your back, your legs, and then to the ground. All right. So your head, neck, back, shoulder, whatever it is, they are parts of you, or they are what you call the fibers of the material, right? In this case. So it means that if a part of you, if your neck is hurting too much, the bag will fall down. If your knee is not too strong, it might buckle. The bag of cement can still fall down, or even you, the person can also end up falling down. All right. So what we do as engineers is to find out if every part of the body can carry the load. So we bring that same idea to the beam. So we need to find out if every little piece within, let's say in this case, the wood, since I'm using wood, if every little piece of the wood can carry the load. So then how do we do that? By looking at the internal behavior. So we take every little or every single point along the entire length of the beam, and then we determine the axial force to see if it's strong enough in the axial direction. They also look at it in terms of the shear to determine if it's strong in the shear direction so that there will not be any slicing effects. And also we look at the bending behavior to ensure that our beam will not overbend or it wouldn't bend too much, whereby it can fail as well. Right. And to determine the internal behavior, which means that pretty much if you want to determine the internal behavior, so we cut sections along the beam. Okay. So for example, so you take this, you cut as many sections as you can, all right? So, or you can cut all these different sections, as many as you can. And every time you cut it, you have a left-hand side, all right? And then a right-hand side, okay? So pretty much when you are cutting a section along the beam, it means that you are trying to focus on a point, all right? So let's say this is point 1, point 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So on at every point, you are looking at the internal behavior at every point, okay? And to help us to easily calculate these internal behavior, we use a sign convention. We use sign conventions. What's just happened to my... Give me a second, boss. If this comes back. Yeah. So we use sign conventions. Okay. And the word convention here simply means that an agreed process or an agreed procedure. All right. It doesn't make a different process wrong, but this is a process that we all agree with. And as engineers, we also need to agree to one style of doing something so that it is easy for any other engineer out there to be able to understand what one engineer is doing or what the other engineer is doing. All right. So we usually have a lot of these agreements, okay, in terms of how things should work. Okay. So one of these has to do with the sign convention for um, these internal behavior. Okay. So I think we said that if we have a point, so let's say this point can be point 1, point 2, point 3, all the way to point 11, like what I have in this case, all right? So if you have a point and then you have your axial forces, let me use a different color, axial forces going away, I'm going towards the left, on the left of the point, we call that positive, okay? Um, And then so if you have it on the right going towards the other side, then it's positive. And so these are positive. And if you have it, so again, the same point here. So if you have it going towards the right and it's on the left, it is negative. And then going towards the right, on the right is negative. Yeah, it can be a bit funny, but then I think I spent a better time last week to explain that to us. So this is, what am I doing? This is negative. So this section is negative. Okay. And this section is positive. Okay. Once we start looking at some examples, it will become a bit clear. So in terms of the shear, so this is for axial. We have shear, and then we have the bending moment. So with a shear, if you have all forces on the left of the point going upwards, they are positive. If you have all forces on the left going downwards, they are negative. All right. Then, so here, pretty much at this end, you're dealing with the left-hand side. It's also the left-hand side. This is the right-hand side. This is also the right-hand side. We just see how everything comes, works out eventually. Then this, we have this as a, let me just draw them and then we can look at them with some examples. All right. Then with the bending moment, any forces or that are causing bending or any point moment, if they are acting counterclockwise and they are if they're acting clockwise, sorry, and then they're on the left, then they are positive. If they are acting what's the name? Counterclockwise and then they're on the right, they're also positive. If they're acting clockwise and then they're on the right, it's negative. If they're acting counterclockwise on the left, it's also negative. Okay. Let me just use an example to explain the concept to us so that we appreciate it a bit more. Okay. Let's look at some examples of how these things come about. So let's start with a basic example. Um, let me make sure that my chart is working. All right, so if I have this, can someone give me an answer? I have a load here. This is 40 kilonewtons. This is 10 meters. And then this is so let me change my load to 30 kilonewtons. This is 20 meters. Okay, so this is A, B, and C. What are the support reactions? Okay, so that's our first question. We are yet to solve anything related to what we are looking at today. Okay, I mean, this is from last week, all right? So we have a free body diagram, all right? So that is one of the most important things that we always have to do with respect to structural analysis. We need to indicate what our reactions will be, all right, with respect to our loads as well. Okay. So this is VB, VA, HA. All right. And then we have the load of 30 kilonewtons, sorry. All right. So can you guys tell me what the values for the support reactions will be? Anyone? Let's resume. Okay. So let's just go through this process. Okay. Summation of forces in the horizontal direction equals 0. So our HA equals 0. Then summation of forces in the y direction equals 0. So we have three of those forces. We have the load, the two reactions. So these are vertical forces, all right? So we sum them up. Okay. And direction-wise, some are going upward, some are going downward. So we need to ensure that we capture that direction differences, right? So we can say that, okay, let VA, which is going upward, be positive. Let VB also be positive, and then let the 30 coming down be negative. Here, you choose whatever you want, right? So this is 0, which means that our VA plus VB will be equal to 30 kilonewtons, all right? We need to find these guys. But in this case, we only have one equation, so we need a second one. And that's the reason why we have to take moments about a point. Let's say in this case, about point A. So we sum all moments about A, and that summation should be equal to 0. Okay. What this simply means that there's no rotation of the beam, or there's no, there's no rotation of the beam about A. Okay. So here I have VB times 30, which will cause an anti-clockwise or a counterclockwise rotation about A. Then plus sorry, not plus, minus, let me use a different color, minus 30 times 10. Right. If you don't understand what I'm writing now on the screen, please send me a message right away. Okay. That's it. Aside the two new guys, if you have been in class since day one and this is strange to you, please text me right away. All right. Or you can send me a WhatsApp message. And is my phone here? Yeah. You can send me a WhatsApp message, private one. I mean, so at least I know, or we know what we have to do about it. All right. Okay. So this is going to be an sorry, going to be clockwise in terms of, am I correct? This is that, sorry. Okay, great. So this is going to be clockwise, this is anti-clockwise. So that's the reason I have the minus, because one of them is opposite the other in terms of the directions. So we have 30 VB will be equal to 30. And this is usually 30 kilonewton meter. All right. So VB will be 30 over 30. Am I doing the right thing? Oh, 300. Sorry. Okay. Today, my brain is a bit slow. So that'll give me 10 kilonewtons. All right. So VB is 10 kilonewtons, which means that our VA will be 30 minus 10, and that'll give us 20 kilonewtons. All right. Great. So we all have our reactions. Now let's go to the second stage. Okay. Now let's find shear force. Okay. And shear force, we find shear force along the length of the beam. So it can be any point. So let's find shear force at different locations. So let's say one at 5 meters from A. Okay. Then two, let's find a shear force at let's say 15 meters from A. All right. Then three, we find a shear force at 10 meters from A. Okay. Then four, we find a shear force at 30 meters. Do I have 20 in there? So let me do 15, 20. Let me do 25. And then, so all from A. I mean, from point A. Then I can do at, this must be at, my A is not appearing. Okay. Um, this is at, so let's do 10 meters because that is an important point, critical. And let's do at number 6, 30 meters from A. Then let's do number 7. Okay. We just see how everything looks like. Then at 0 meters from A. Okay. So going back, 10 meters from A is point C. All right. And then 0 meters from A is point A. Then 30 meters from point A is B. So I'm just going to put that into bracket here. So this is point C, this is point B, and this is point A. All right. I don't need the. So let's take our beam again, right? So now we found all our reactions, so we know how the beam looks like. Okay, so we have these reactions. Okay, so HA0, so I can forget about that. So this is I have a load here. This is 20, this is 10, this is 30. Okay. So here I have my 10. So this is 0. This is 5. This is 15, 20, 25, and 30. All right. So let me just go by this. So the first thing is that I want to find my shear force at 5 meters from A. All right. So anytime you want to find an internal behavior, you have to cut the section at that point. Okay. So it's going to be a lot of writing, but you'll see that things keep repeating. Okay. So let's look at the part 1, which is so shear force 5 meters from A. Okay. So I take my structure as we have it. It's always easy to make copies. Okay. And I cut this section along the 5 meters. So I'll have two parts. I'll have a left-hand side and a right-hand side. Okay. So if I'm to work with, assuming I'm working, so let's say working with the left-hand side, okay? You can also work with the right-hand side if you want, but it has to be one or the other, not to both of them, okay? Because if you do both of them, you would end up with the same answer. So why waste time to repeat, right? So either is fine. Mostly we go with the left-hand side. There are a few instances where the right-hand side will be the easier approach, all right? And going forward, we might see some of these examples. But on a normal day, every day, usually, the left-hand side is the easier one to go with. So it means that I'll be looking at this zone, all right? So let me draw that part again. Okay. What do I see on the left, I say this 20 kilonewtons. And because I cut this section into two, it means that I have broken apart that equilibrium behavior, which means that I'm going to see, so normally we prefer this to go downwards on the left, and I'll see this, and then I'll see the bending moment as well. Okay. I'll say this bending moment. So the bending moment M, the axial force, and then the shear force. All right. For now, I have interest only in the shear force because that's what I'm looking for. All right. So how do I find the shear force? Okay. Sum the forces. All right. So one of the easiest ways is to sum all vertical forces. So go like summation of all vertical forces equals 0. Right. So 20 is upwards. Okay, let's look at something for now. 20 is upwards minus the shear force at 5 meters. So SF5, okay, equals 0. So SF5 will be equal to 20 kilonewtons. All right. This approach is fine. Let me put that into brackets. And then let's use the sign convention. Okay, the sign convention method. So let me put here a big O. I think I can write on the left hand, on the right hand side, when the O will be on the right hand side, so it's fine. Let me see. Okay, I think I'm good to go. Let's have the O over here. Now, sometimes this is what we, this is the reason why we need the sign convention, okay? So on this side, you have your 20 kilonewton, right? Okay. Okay. I'll go over that shortly. Okay. So now we want to find the shear force at this point. All right. So we want to find the shear force, which you call the shear force at 5 meters away from A. All right. So this is the point we are looking at. Okay. So to find the shear force at 5 meters from A, so here, with the second option, I didn't put any direction for the shear force. Right, great. Now, if you go to the sign convention, okay, the 20 kilonewton, let's look at it carefully. This 20 kilonewton is what acting upwards. Okay? And it's also on the left of the point. Okay. Whereby this point is the 5 meters. Okay. So it is acting upwards and on the left of the point. Now let's go back to our sign convention and see something. Okay. So here our focus is on the shear. So we are looking at only shear, right? Oops. This is a terrible way to shade. So we are looking at the okay. So we are looking at shear. Now we said our shear, the 20 is acting upwards and it's on the left. So if it's acting upwards and it's on the left, then it means that we are looking at this guy here. This is what conforms to the 20. It is acting upwards and it's on the left. So that makes the 20 positive. All right. So 20 is positive, and this becomes, in this case, this becomes your shear force. All right. Going forward, this will be the approach. Um, any of them is correct, all right? But this approach is used because it helps us to develop equations to determine some of these internal behavior, all right? Uh, in the beginning stage, uh, we can use the one on the left as an example for basic calculations, but going forward, it becomes a bit more tedious to do that. Um, so here, if you're looking at what I did with this portion, let's say option one, you would see that with the option one, I specifically chose my shear force, I mean the internal behavior, to be acting downwards. All right. I chose that because I understand the sign conventions quite well. And from experience, once these are our sign conventions that we have, whatever I wrote up earlier, it means that when I'm dealing with the left-hand side, my shear force would always act, or the unknown shear force would always act downwards, regardless of whatever forces I have on that left-hand side. Okay. Um, let's do a few more, and then let's see how things work out. So let's look at 15 meters. So I take this whole thing here, and I do this part of the course is one of the more confusing parts. I believe not that it is extremely difficult, no, far from it. It is not difficult. It can be a bit challenging. Uh, so I'm taking my time going through the phases of it, so that if there are any questions, we are able to capture that and then resolve them. Then at least be able to grasp the process involved in these types of analysis. So here, let's say that, oops, let's say that now instead of, okay, take up deleting too many stuff. Okay. So now we want the shear force at 15 meters from A. So 15 meters from A will be somewhere here. All right. So we are going to cut our section into two parts, the left-hand side and then the right-hand side. This is the part we cut through. Okay, so there's a cut section here. Okay. So it means that with the left-hand side, I'll have something like this. Okay, so what do I see? I see the 20, and also I see the 30. That is what is on the left-hand side. Okay, so this is the point of interest to me. Okay. So I want to find the shear force at 50 meters from A. So here I'm going with the second option so that at least we get the understanding of it. So the shear force at 15 meters from A will be, so let me put into this space the sign convention so that at least we have them. Okay, it's fine. Okay. So this is a point we always use as our reference. And then we try to figure out, so here is left-hand side. This is right-hand side. Okay, left-hand side, right-hand side. Okay. So here, since we are working with the left-hand side, It means that we will be looking at anything that is left-hand side. Okay. If you are choosing the right-hand side of the section that you cut to work, then you would have focused on the right-hand side conventions. Okay. So now you look at these, your forces, and see whether, so this is positive, sorry. And this is negative. Okay. Then you see which of them negative or positive, all right? So if you look at the 20 kilonewtons, all right, anyway, all the forces are acting on the left or to the left of the point, the SF15, all right? So the 20 is acting upwards, all right? So upwards on the left is positive, okay? So that makes my 20 positive. So let me put a big plus in front of it. The 30 is also on the left, but it's acting downwards. So that makes the 30 what? Negative. All right. So it becomes minus 30. So that if you sum these two up, you get what? Minus 10 kilonewtons. Okay. So the shear force at 15 meters from A, it's minus 10 kilonewtons. Okay. So that is the one, like, I mean, this is how we go about it. If this seems um, a little too strange to us, we can then go by the one I mentioned earlier. So whereby, let me just put that one on this side. Okay. Whereby you indicate the direction of your shear force. Okay, which is going to act downwards. And in this case, you are summing up vertical forces only, right? Yes, there'll be the bending moment, there'll be the axial and all of that. But usually if you are summing up um, vertical forces, only vertical forces get summed up, right? So normally when we are dealing with shear forces, you see that we usually neglect the other unknowns because they don't really add up to the shear force. All right. Shear force simply means that vertical forces, at least with regards to beams. Okay. So here, if I'm summing vertical forces, uh, so if I sum vertical forces, I'll get what? 20 going upward, minus 30 coming downwards, then minus the SF15 coming downwards, and that'll give me 0. Okay. So I need to make the SF15 the subject. So SF15 will be equal to 20 minus 30, and that is the same as minus 10 kilonewtons. Okay. They both are the same. They both work out quite well. Okay. So we're done with 1 and 2. This is 2. Now let's look at 3. 3 is at 25 or at 20 meters from A. I think I'll jump the one of them so that we can have this thing done. So let's say at 3, we are looking at 25 meters from A. So let me take you out, take you out, take you out, take you out. Okay. So 20 meters from A, that is 3. So 20 meters from A will be here. Oops, will be here. So we cut the section along this side. Okay. So again, we are dealing with the whole. So both solutions can work out, right? So going back, solution A, solution B, they both can work out. All right. They both can work out. The reason sometimes you are careful with solution B is that if you mistakenly change the direction of your shear force, right? on the left hand side, it's supposed to be always acting downwards. If for whatever reason, you tend to forget that it's supposed to act downwards, and then you change it to act upwards, it means that your shear force values are wrong. All right. So, and the reason why I said that I don't subscribe to it, because under a lot of examination pressure, and then all of that, you tend to miss a few things. The sign conventions, I mean, the solution B is still based on the sign conventions anyways. Let's get that also done. It's based on the sign conventions, but just that you don't explicitly use the sign convention for solution B, right? It's implied, but you don't use it explicitly. But with the solution A, you have to use the sign conventions. Okay. So we only choose the area the force is acting more on. I don't get your question. If I'm to understand it in my own way, when you are looking for the shear forces, all right, or axial or bending, whichever one you are looking at, you have to cut the beam into two parts at the point where you want to find the shear force, right? So if you cut a beam into two parts, now you have two separate parts, one on your right-hand side and one on your left-hand side, all right? You can use any of them to find the unknown internal behavior. Okay, so you can use any of them, preferably the left-hand side works, all right? Or the left-hand side is easier because of the fact that normally when we are writing, we write from left to right, basically, right? So the way the brain is wired, left to right, works most of the time for our brains. Okay. So that is an easier process. All right. So any of them works. Left hand side is easier because of how our brain is wired. Okay. So here, if I choose, so have my, so this length here is 20 meters. All right. So again, I have my VA, which is 20 kilonewtons. Then at somewhere 10 meters, I have the 30 kilonewtons. And I need to find my shear force at 20 meters from A. All right. So shear force at 20 meters from A will be equal to the 20 kilonewton load, which is the VA, minus the 30, and I'll still get minus 10. Okay. Or you can use the other approach, whatever, if you have this acting downwards, and it's the same thing. All right. So you will see that there are some patterns being formed. We'll look at it. This guy is too big. Reduce the size a little bit. Okay. So here, let's say 25 meters. You have that 25 meters. This is 4 from A. So we will move our cut section to 25 meters from A. All right. So again, we have the left-hand side and then the right-hand side. Okay. Since we've been dealing with the right-hand side throughout, I'm sorry, with the left-hand side throughout, we maintain that be careful when you are dealing with some of these things. That it's not wrong, but when you try to do maybe some part of the questions, you deal with left-hand side, other part right-hand side. Be careful because sometimes it can be a bit confusing. It's not wrong to choose some left, to choose some right, but if you maintain conformity throughout, you are less likely to make mistakes. All right. But then as you gain more experience, then you can interchange them as you go along. Okay. So here I have my beam up to the 20. So I have my 20 kilonewton meter, sorry, kilonewton over here. I have my 30 kilonewton also. And the distance here is 25 meters. So I want to find the shear force at 25 meters at this point. Okay. And we are saying that the shear force is always acting downwards on the left-hand side. So this means that my shear force at 25 meters from A will be equal to 20 minus 30, and that is minus 10 kilonewtons. Okay. So I think we've done 1, 2, 3, 4. Now we've gotten to the critical part, which is the 5. So that is 10 meters from A. Okay. So let me just copy and then paste again. Okay, so here is where things take a slight turn. This is 5 or maybe 6. 10 meters from A. So 10 meters from A is exactly where our load is acting, that same point. So we want to cut here. Okay. So what happens? So I take this. Okay. So here's my 20. Now, why is the cut section not added? The sign convention, since the force is acting upwards there. Which cut section? Oh, please, so this cut section, please, this is not a force, it's an arrow. Okay, this is an arrow. Here is an arrow. Okay, let me just not draw it straight. This is an arrow, okay? It's just an arrow to show us that we are cutting over here, please. It's an arrow. Okay, this is an arrow, not a force. Arrow again, not a force, please. So this is an arrow. Yeah, I know the arrows and forces look very similar. This is an arrow, okay? Let me make sure that we capture that as well. This is not a force, this is an arrow to show that we are cutting here. All right. So this is an arrow, please. This is not a force. Where again do I have that? Okay, no more. It's an arrow. The only force we are dealing with is the shear force acting downwards. Okay. So it's an arrow, please. Again, arrow, arrow, arrow. Okay. Now we have a problem. Okay. If you look at it carefully, we are cutting the section at 10 meters from A. Yes, so now the 30 kilonewton load is acting exactly at where we're trying to cut the section. So what do we do? Do we include the 30 or we don't include the 30? All right. What do you think we should do? Can someone give you an answer? I mean, just guess something. Should we include the 30 as part of the load when we cut the section, or we shouldn't? All right, so I've got an answer saying that I should include it. Anyone else with any different answer? I mean, it's either one or the other, right? It's either MPP or NDC, right? Okay, now I'm getting a maybe. Some say I should include half. Okay. That's a nice answer, TT. So we should include half. Some also saying we should include that all. Okay. Now this is an interesting thing, right? So I'm going to draw for both of, I mean, the two answers which I think are likely. So this is 20, and here I have the 30. Okay. So here did not include load at cut section. And here load at cut section included. And the interesting thing is that both of them are correct. Both answers are correct. Not including or including, they are both correct. So if we don't include, so shear force at 10, this is again also shear force at 10. So if we do not include, our shear force at 10 is equal to 20 kilonewtons. If we include, our shear force at 10 is equal to minus 10 kilonewtons, right? Because it is what? 20 minus 30, all right? So minus 10 kilonewtons. Both answers are correct. And the reason behind all of this is that when we were discussing shear force, we mentioned that shear force causes what? A shearing behavior, a slicing behavior, all right? Which means that at any point you come across a point load, which is what's the name? It can be an external load or whatever. That external load will cause that slicing behavior. All right. So anytime you come across an external point load, we need to what's what I'm looking for? We need to show, or we need to capture that slicing behavior. And the only way we can capture that slicing behavior is by looking at the shear force value with and without that particular load. So here I can say that shear force before and then shear force after, and they both are correct. Okay. For now, let's leave it this way. We'll come back and then see how things finally look in the end. Let me do the last two. So it's 30 meters from A. So at 30 meters from A, we have something very similar to what we had. So let's clear a few things. This is 30 meters from A. So here we have to cut this section right here. So cut here. Again, we are running into a similar problem as we had with when we cut the section at where the 30 kilonewton load was acting. All right. Pretty much when you see a shear or when you see a point load, the point load is what is likely to cause the shear behavior, that slicing behavior. So to capture that, you need to look at the shear force before that vertical load and then the shear force after that vertical load. Okay. So here we'll have two cases. Okay, so I call one before and the other after. All right. So in this sense, I'll have a whole system in place where I have my 20 kilonewton load. I have my 30 points load. Then I don't include my 10 at the end. I only find the shear force at 30. All right. Then I have the second case whereby I have everything I need. So this is my 20 kilonewton. I have my 30. I have my 10. And then I have my shear force also at 30. All right. So in the first case, my shear force at 30 will be 20 minus 30, which will give me minus 10 kilonewtons. Then in the case 2 or the after, my shear force at 30 will be equal to 20 minus 30 plus 10 equals 0. So the shear force at 30 after the point load is 0. Okay. Now let's look at the last one. Uh, I'm just going to do something. So with the last bit, which is so this is like 6 or 7 maybe, and then this is at 0 meters from A. So that is point A. So here we cut this section right here. So cut here. Oops. Okay, all right. So here we also have cases, not one case, not two cases. Okay. So here we also have, because we are meeting the point load, we also have that same issue. Oops, should have taken this guy out. Okay. So before, okay. So if we cut a section before the 20 kilonewton load, it means that our shear force at that point will not have any value. So the shear force here at 0 will be equal to 0, or the shear force at A will be equal to 0. Then just after, when we cut the section where we include the point load, which is the 20 kilonewton, now our shear force at that point then becomes 20, because the point is on the shear force is on the left. Sorry, the 20 kilonewton load, the reaction is on the left of the point SF. So it becomes 20. Now let me put all this into a table. All right. So at least we see what we are looking at. So the distance, so let's call the distance along the length of the beam X. And let's call the various shear force that we had. Now when X was 0, okay, we have two values. We have shear force being 0 and then shear force being 20. Okay, they both are correct. Now when let me just try and put a few lines in place. Or am I struggling to get this thing taken care of? Okay, so let's do it this way. All right. Now, when when X or the cut section move to, I think 5 meters, our shear force was what? 20 kilonewtons. All right. Then when we move to 10 meters, again, we had two values. We had 20 kilonewtons, and then we had minus 10 kilonewtons. Okay. When we move to, I think 15 meters, we had only one value, minus 10 kilonewtons. Then when we moved to 20 meters, we had also only one value, minus 10. And then I think the whole thing keeps going on and on. Then I think at 25 meters, we also had minus 10 kilonewtons. And then at 30 meters, we had two values, minus 10 kilonewtons and then 0 kilonewtons or 0. Okay. Now, this can be used to plot a graph. All right. We have our x-axis here. Then we have our y-axis over here, or the y values, anyways. So we can draw a table, or we can plot a graph through this. Let's see. Let me use my graphing skills over here. So let me just have this guy. Okay, so let me see. 5, 10, 15, 20, 25, 30. Okay, this is okay. Um, okay, so let's say we have this. Okay, so this is 0, 5, 10, 15, 20, 25, 30. Then here, I'm going to go a bit. So I'm just drawing my x and y axis. All right. So here I have. So this is 5, 10, 15, 20. Here I have 5, 10. Let me drop to 50. So this is my negative, and over there is my positive. All right. So now let's see how this whole thing is going to turn up. Oops, come back. Okay. So let's look at it. So let's start with this point here at the 0 point. So at the at when x is 0, we have two values for y. So one value is oops, let me use red. One value is 0, and the other value is what? 20. Okay, good. When x is 5 meters, it is 20. When x is 10 meters, we have both 20 and then we have negative 10. Okay. When x is 15, we have negative 10. When x is 20, we have negative 10. When x is 25, we have negative 10 again. When x is 30, we have negative 10 and then 0. All right, so let me just put it down and say this is, so here's 0. This is 20, 20, 20. This is 5. Sorry, this is 10, not 5. This is 10, 10, 10, 10, 10, 0. I mean, 10, that's it, negative 10, all right? This guy looks like I'm off a little bit. Why do you keep deleting? So this is minus 10. Let's put it here. Okay, great. So now let's try and join everything and see how they look like. So just join the points, okay? So where's my ruler? Okay, it's here. So I take my ruler and I join the points. So from 0, it jumps to 20. Then it maintains itself throughout straight. Then at 10 meters, it drops again. Sorry, my I didn't get my diagram to look straight. It's fine. And then between 10 and 15, sorry. So 10, 15, 20, all the way to 30, it still remains straight. Then just at the very end, oops, let me see. Okay, I'm just gonna join them, okay? All right. So just so that we don't get big of him, just move this guy here. Oops. So in effect, this that I have drawn here, this diagram here, which I can redraw it in a much more simple process. Okay, so here's 20 and here's 10. This is negative, this is positive. This diagram here, either of the is called the shear force diagram. Okay. And this gives us an idea of the shear force behavior along the entire length of the beam. Okay. You see, we couldn't do 0 meters, 1 meter, 2 meter, 3 meter, keep doing every meter to 30 meters. That will take forever, right? So usually you do the intervals or you do the shear force for some intervals, and then you try to capture the key points along the beam. They use that information to draw your shear force diagram. Right. Any questions? Are there any questions for me? All right. So this is in this simple terms how we do the shear force diagram calculations. Okay. Yeah. So please, I just drew this to for us to see it like on its own, but this is fine if you do this whole X and Y axis and all of that, and you show the different grading points. This is the shear force diagram. All right. And because I didn't want to have the X and Y shown as I drew it separately on the other side. But um, the diagram is drawn from your shape, right? So when you do your calculations, whatever you get is what you use to draw your diagram, all right? The more we draw, the more we'll see some patterns being developed, all right? Today, I think we have about what time are we? We have about 1 hour more. So we'll take about some 10 minutes break from now, stretch our legs and come back, and then we can continue for another 1 hour. And then we should be done with today. All right. Uh, Now before we go on a break, let me just show you something briefly, and then we can see that there are some patterns being developed. Okay. It's really easier to use uh, the table. All right. So there are a few things that you'd see as you go along. You'd realize that shear force, if there are supports at the end, like in this case where we have supports at the ends of the beams, shear force will usually start at 0 and then jump to the value of the reaction at the support. All right. So if you looked at it, we initially had, just gonna show some patterns so that we appreciate what is going on. So we had 20 here, 10 here, and this was 30. Okay. So this was our VA, this is our VB. All right. So the shear at the reaction, it jumps to what? Uh, VA, right? Or it is VA. Okay. It is VA. So the shear over here is VA. The shear over here is VB, or is a negative of VB. All right. So if you look at it, between 0 and 10 meters, our shear force remains the same, right? So I can make some few deductions. So in between point loads, okay, so in between point load means there are no loads. Where there are no loads, so if there are UDLs, then this will not work. All right. So where there are no in between points loads, where there are no loads, shear is constant, or shear force is constant. Okay. So we can see that example in this space right here. Oops, wrong shading choice. So between A and 10 meters, the shear remains 20. Again, if you look at it between the 30 and then the 10, the shear also remains constant. Okay. So usually in between point lows, the shear is constant. So let me take you back to, is it math, your math class or so? I think core math or something like that. When you have an equation of a line, lighter out. So before the break, I mentioned that if we look at our shear force, you'll realize that there's a pattern being developed. All right. And I mentioned that if you look at it between loads or between points, okay, between loads, right? Between loads, which means that those sections do not have any loads in there, the shear force value is constant. All right. And we saw that with with the example that we just worked on. We'll go ahead and do a few more examples to develop a pattern in there. Um, okay, so just to let me go over what I was saying before the break again. So that I mentioned that if you look at going back to our section, if you look between the support reaction at A, which is the 20 kilonewton load, and then the load acting on the beam, the 30 KN load. Between the two, there's no load between the two, right? I mean, there's no load between these 2 points loads, all right? And because there's no load between these 2 points load, the shear force also remains constant between those two. Okay. So with this example, our shear force is 20 kilonewtons, which is pretty much the shear force between the reaction at A and then the points load at C. All right. And again, between C and B, there is no load. Okay. So between C and B, there's no load. And when there's no load, your shear force value remains constant. Okay. So that's what I was trying to say before the break. And I also mentioned that back in your math class where you had to draw lines, right? A series of lines. The equation for a line was y is equal to mx plus c, right? So this is a linear relationship, right? Where I think m is the gradient. So the m here is your gradient or the slope of the line. Okay. Then c is supposed to be a constant. Okay. So in the case where the gradient of your line is 0, then it means that your line is simply y equals what? C. Assuming that c is not equal to 0, then this is the equation of your line. And usually for such a line, this is how we draw such a line, where the gradient is 0. Let me draw with the red. Okay, so this is a line where y is equal to c. And pretty much this is what we are trying to do over here. This is constant. This line here is constant. This line here is constant. Or the equation of the line is constant because of the fact that y is equal to c. So between points where there are no loads, the equation of your line is a constant. Let's leave it as it is for now, and we'll come back to it. There are so many angles you can look at these diagrams, okay? So I want you guys to be aware of the different ways by which we can look at this diagram, so that going forward, once we start dealing with equations specifically, all these will come into play. Okay. Now let's look at another example. We just look at some one or two examples, and then we should be done with today for the course. Okay. So let's say we're looking for them. Use the examples in our notes. So please, there is like a well-detailed example in our in the lecture note I posted. I mean the typed one. There's a well-laid example which also expands on what we've been discussing so far. All right. So I would advise you also have a look at that as well. Okay. Let's say we have this. Okay. Then on top of it, we have a UDL. Let's say the height of the UDL is maybe 2 kilonewtons per meter. The length of the beam is maybe, let's say, 10 meters. Okay. So these points are A and B. Now I have another question for you guys. Find the support reaction. Okay, so that's the question I have for you guys to solve right now. Find the support reactions. Okay. So to draw the free body diagram, I have this as my beam. These are my loads, or my reaction, sorry. So this is my HB, VB, VA, and then the UDL is on top. What are the reactions? So you can send your answer to, as we did earlier, something very similar. So let me know of your answer. Okay, I think quite a number of us have been able to join. So I'm pausing recording for like 2 minutes and send me your answers. Again, Nelson, again, if for some reason this seems strange to you, please let me know and let's see how we can help ourselves, okay? So with this one, summation of horizontal forces equals 0, so HA is 0. Then the summation of vertical forces is equal to 0, so we have VA plus VB minus, so we need to convert the UDL into point load, so it becomes 2 times its loaded span. That will be 0. So VA plus VB is equal to 20 kilonewtons. Okay. This is a typical symmetrical arrangement, so the answer will be VA 10, VB is also 10. All right. So summation of moment at A equals 0. So we take VB times 10 meters minus 2 times 10 for the UDL times 10 over 2 equals 0. So VB will be equal to 10 kilonewtons. Okay. The other way to look at it, let me just have this on the side. It's always good to have some few things on the side. If this is W, right, and I have this here, my VA is WL over 2, my VB is also WL over 2. Okay. So that if this distance here is L, all right, so this is a typical, what you call a symmetrical system, where the entire beam has been loaded for a simply supported beam, so that VA will be equal to, the W is 2, the L is 10 over 2, and that'll give me 10 kilonewtons. Okay, so this is just on the side. Sometimes it's good to have these ones up so that at least we appreciate what goes on. Okay, so now the same way that we found the shear force along the length of the beam for the first case, we'll do something very similar. All right, so this we'll do it at 2 meters intervals. All right, so that we appreciate what is going on. So I'll try and make this one shorter. So let's say shear force at 2 meters. Okay. So again, so what that simply means that you take your beam, you cut a section at 2 meters from the beam. So if I cut a section, I'll get my left-hand side. So this is my VA, which is 20. So let me just put it at VA is 20 kilonewtons. So at 2 meters, I have this. All right. So this distance here, oops. The distance here is 2 meters. Okay. Then I have my VA, where VA is known as 20 meters, right? So I want to find my shear force at this point. Okay, which is this right here. So the shear force at 2 meters. Okay. So the shear force at 2 meters will be equal to what? VA minus the UJ, which is 2 kilonewtons per meter. So it becomes 2 times 2 meters. All right. And our VA is what? 20, right? So this becomes 20. Our VA is 10, sorry. Becomes 10 minus 4. This will give us 6 kilonewtons. Stop me at any point you want to ask your questions, please. Now the shear force at 4 meters. So let's do at 4 meters. Okay. So we'll see a pattern being developed. So at 4 meters, we have again our VA. Then we have a UDL. And this distance here is 4 meters. And we want to find the shear force at 4 meters. So the shear force at 4 meters again is what? VA minus 2, where 2 is the UDL height or the intensity of the load. So 2 times a distance of 4. So this will give us 10 minus what? 8. And this is 2 kilonewtons. Okay. Now let's do the shear force at. So I'm going to go to 5 for now. I'll come back to 6. So at 5 meters, again, we cut our section at 5 meters. So we have our UDL again. This distance here is now 5 meters. We want to find shear force at 5 meters. So shear force at 5 meters will be equal to VA minus the UDL intensity times 5. So this is what 10 minus 10, and that'll give us 0. Okay. Now let's do shear force at 6 meters. Right. So you can see that things look very similar. This is 6 meters distance. We want to find the shear force at 6 meters. So shear force at 6 meters will be equal to VA minus 2 times 6. So that will be 10 minus 12. This will give us minus 2 kilonewtons. Now let's do one more. Shear force at 8 meters. Okay. Again, take our section. Too long for 8. Okay. Again, we have our UDL on it. Right. This is supposed to be 2 kilonewtons per meter, as we had it earlier, with a distance of 8 meters. So we want to find our shear force at 8 meters. So SF8 will be equal to VA minus 2 times what? 8. This is 10 minus 16. That'll give us minus 4 kilonewtons. Okay. Now, shear force at 0 meters and shear force at 10 meters are special, right? And they are special because we have a point load over there, okay? And just in the first case, when we have a point load, what do? We find the shear force before that point load, and then the shear force after the point load. Okay. So before the point load, and then after the point load. Okay. And the reason for that is so that we can capture, the shearing effect or the slicing effect. Oh, it's minus 6, yeah. At 8 meters, it's minus 6. Yeah. Oh, yeah. Thanks for the correction. Okay, thanks for the correction. All right. All right. So these are the points to look at. So I'm going to do shear force at 10 meters. Okay. So at 10 meters, this is what we have. So we have our load, our UDL on it. Okay. So in case 1, which is the before, we are not including the punch load at the end of the beam. Then case 2, which is after, we have so the same thing, all right, with the UDL. We show the VB, right? So case 1, no VB. Case 2, or should not, I would say case 1, case 2. I mean, like option 1, no VB, option 2, VB, and we still want to find our shear force at 10 meters, our shear force at 10 meters, right? So with this guy here, our shear force at 10 meters before will be what? VA minus 2 times 10. So that'll be what? 10 minus 20. That'll give us minus 10 kilonewtons. Okay. Then for the second option, it becomes VA minus 2 times 10 plus VB. All right. So here I'm still using the whole what's it? The sign conventions, right? If it's on the left of the point of interest and it's upward, it's positive. If it's downward, it's negative. Okay. So always have this at the back of your mind. So this is positive and this is negative. All right. So I've been using this ever since. So here my shear force at 10 meters becomes 10 minus 20 plus 10 equals 0. Okay. So a similar thing will work for the shear force at 0 meters. So let's draw our diagram. Let's just draw our shear force diagram just to see how things come out. Okay. So let me just do 2, 4, 6. Let me put 5 here, 8, and then 10. I think I had them in multiples of 2, eh? 1, 2, 3, 4, 5. Okay. So 2, 4, 6, 8, and 10. So again, 2, 4, 6, 2, 4, 6, 8, and then 10. Right. So this is your x-axis, and this is your y-axis. All right. Okay. So this is minus y, and this is plus y. Great. So let's see. So let's go back. When you had it at 2 meters, your shear force was 6. All right. So just going to look at it. So at 2 meters, it was 6, so somewhere here. Okay. At 4 meters, it came down to 2. Okay. All right. At 5 meters, it came down to 0. At 6 meters, it became minus 2. So somewhere here. So this is minus. Okay, let's just take a note. Then at 8 meters, it was minus 6. All right, so minus 6 is somewhere here. Then at 10 meters, all right, I didn't bring 0 for now. I'll take the 0 in there. At 10 meters, we had two values, right? We had minus 10 and then 0. Okay. In the same way, at 0 meters, our shear force will have two values for it. We'll have one being 0 and one being 10 kilonewtons. It's the same idea. So at 0 meters, 10. Okay. So that'll be somewhere here and then here. Okay, so let's try and join the lines and see what we get. So if I'm to join the lines, so I have here, this will be my line. Then if I'm to join this point, it will be a straight line. My points are not passing through, but for most of them, but this. Let me just make sure they pass through them. Okay. So this is how it looks like. So here I'm only plotting points. So I have the straight line here too. All right. So in simple terms, this is how it looks like if I'm to extract it. So it's a straight line, pardon me. Oops. Another straight line. Okay. So here's 10. This is 10. This area is positive. This area is negative. Okay, so this is um the shear force diagram. But in this case, our load is a uniformly distributed load. So because our load is a UDL, because our load is a UDL, the shear force diagram is a bit different. Okay. And let's look at some patterns that were developed as we were looking for the shear force. Let me put that into this bracket. Right. So this one became what? Shear force is equal to VA minus 2 times what? X. Right. So when X was 2, this was our equation. When X was 4, we got 2. When X was 5, we got that. When X was 6, we got this. When X was 8, we got that. All right. So I can look at what I have done so far and I go like my shear force at any point X is equal to VA minus 2X, where these two is the intensity of the UDL. All right. And let's see if it makes sense to us. All right. So let's change the value. So if X is 0, it becomes what? So this is X. It becomes VA is what? VA is 10. So it becomes 10 minus 2 times 0. So that'll give us what? 10 kilonewtons. That is correct. Again, if V is 2, becomes 10 minus, sorry, if X is 2, so these are the X values. All right, these are X values. If X is 2 meters, all right, it becomes 10 to 2 times 2, and that'll give us what? The 6 that we had earlier. So this 6 right here. Okay. Then if X is 4 meters, becomes 10 minus 2 times 4, and that'll give us what? 2 kilonewtons, as we had over here. Then if X is 5 meters, so it gets 10, 2 times 5, and this gives us 0. All right, right there. So let me do one more. If X is, let's say, 8 meters, it becomes 10 minus 2 times 8, and that gives us what? Minus 6 kilonewtons. We had that right over here. Okay. So in a way, we have developed an equation for it. Okay. And this equation is similar to ones that we've seen before. So let's say SFX is equal to VA minus 2X. All right. This is the same as what? Y is equal to, I can change it. I can say, okay, Y is equal to C plus MX, right? The plus or minus, they don't really matter because it can be negative or positive depending on what your gradient will be. All right. And this here is an equation for a line. Okay. Typically, we call it a linear equation, right? So this is a linear equation. So you would see that we drew a line pretty much. So this is a line that we drew. We drew this line right there. So this is a line. All right. So this is the equation for a line. Okay. A few other equations will come up. The reason I want us to appreciate the equation approach is that at some point during the course, maybe not for maybe not too important this semester, but as you go higher, you wouldn't want to be looking for shear forces at every interval. That's right. 'Cause there's a lot more that goes into it, and you wouldn't want to be spending too much time trying to determine shear force at intervals of 2, 3 meters, 4 meters. If you know the equation and you can find the two ends of your line, you can draw your line, right? You don't need to find for every single point along the length of the line. So what we are left to look at is how to draw the bending moment diagram for sections. All right. Okay, let's give me a second.